Okay, so Reifenberg parametrization, and then I'll just change it for a moment, and the analyst traveling salesman theorem. All right, so actually some of you maybe were here at the 15 minutes of talk, so there was like a trailer for this one. So I wanna introduce. We wanna study like parameterization rectifiability, but before that, I wanna just introduce you like the two main objects which we're gonna deal with, and one is related to the Reifenberg parameterization, and the other one is related to the analyst traveling salesman problem. So although this stuff comes from 1960 and this stuff comes from 1990, in my life this stuff arrived earlier than this stuff. So I will like to tell you about beta numbers first. So I wanna define you beta numbers. So Peter Jones, not Betty. There is no cohomology, just beta numbers. All right. So Peter Jones was solving this problem called the analyst traveling salesman theorem, and the question was and everybody know the traveling salesman theorem is an analyst version in the sense that you can have infinitely many points, maybe even uncountably many, or a continuum. And the question was like, what are some geometric characterization on subset of the Euclidean space, so that we can find the Lipschitz curve that passes through them all. So and the curve will be the path taken by the traveling salesman. So maybe okay. So question. I'm not gonna write the question because I want to spend more time later. All right. So let me define this beta number. So basically, the idea is that like if you're a Lipschitz curve, you're very flat almost all the time. So I kind of want some like way to measure how flat you are to begin with, how close you are from being a line. Because if you're a Lipschitz curve, you have tangents almost everywhere. So that's something that I want to recover. So I want to look. So this is my set E, right? So I live in the plane. I have a set E, and now I want to find a measure, a quantitative measure of how wiggly it is. So what I'm going to do is that I'm going to just take a certain scale. So this is a cube because of harmonic analysts like cubes. But if you prefer balls, this can be a ball, and in fact it's gonna be. And now I'm gonna remove this because I don't want to think about it. I'm gonna try to eyeball which one is the line that approximates it best. So I think this one would be like a pretty good line. And now I'm gonna take the strip of smallest width around my set that contains the strip of smallest width around my line that contains all my set inside Q. All right? And then I kind of want to tell you, oh, this is beta. That would be kind of not a great definition because the width of the strip depends on the size of the cube. And I want to measure it like in a scale invariant way. So I want to multiply by the diameter cube. Now, if this is confusing, maybe the formula should help a little bit. So what am I doing? I'm taking the distance from points with a line. Where are my points? My points are in E intersect Q. Which line I'm taking? Well, I'm taking the best line, where I'm taking the infimum over all lines. And then I told you I am dividing by the diameter because I want something scale invariant. I mean, this is a number which has no units, right? This has the unit of length, and I'm dividing, so this one is a scale. And I'm going to call this one beta infinity EQ. And later on, I'm going to start using it interchangeably with cube and balls. And if you have any problem with that, just let me know while I do it. OK. And what is the theorem that Peter Jones proved? OK. So I'm going to give you a much worse version than what he actually proved because of time. But I will write it here, actually. So the theorem is due to Jones in 1990 for R2, for one-dimensional things in the plane, and then it was extended to n dimension in 92 by Okikioğlu. And the main difference in their proof is that one direction of the proof here use complex analysis, and this one use harmonic analysis. And what is the theorem? That if given a set E, let's do like all bounded sets, so we don't think about that. E in the unit cube in Rn, there exists a curve gamma. Gamma contains E, and the length of gamma is finite. In fact, this is analysis seminar, so I can do this. Okay, and if and only if the sum over all dyadic cubes, so let me write it and then you can tell me if you're not happy with this, of beta infinity 3q square is finite. Okay, let's think about it. I'm using 3q, that's not worry about. It's just because to make sure that nothing falls in the cracks. And I'm taking the square of these beta numbers, okay? And I'm summing over all the dyadic cubes. So this means that I'm not summing about, I'm summing, like for every fixed scale, there is infinitely many cubes I'm summing over, and that's why this appears, okay? So, in fact, it does better because and I don't want to spend too much time. In fact, the length of gamma is comparable to star plus the diameter of E. Okay? So in fact, this is not just telling you that it's finite. This is why it's called analysis, because it's like quantitative thing. It's not telling you it's finite. It's also like telling you how you can bound it. This bound is terrible, though. People have tried to like do algorithms. Not great. Okay, so I'm just gonna leave this here, and yeah, and maybe because of time, I won't give you an idea what happens. Okay, so this is my advisor. Advisor is one of the first things I learned in math. That's not true. I learned it like in grad school. I went to college before that, so hopefully I learned something more. And then later on, I learned something which is in fact much older. So let me tell you about. Okay, so Reifenberg, topological, this theorem. Okay, so we're in the 90s. So Reifenberg was working on minimal surfaces and plateau problem back in the 60s. So in fact, he passed away in 1963, and he has an ACTA paper where he provided the first solution for the plateau problem without any topological assumption. We are not going to talk about plateau problem at all, but in the path of proving that theorem, he proved what is now called about topological this theorem. So the theorem, and I will need a definition, but I was gonna show you first before you get lost why it's related to that in my mind. So this is Reifenberg in 1960, says that if E is Reifenberg E, I will stop writing it, but all my sets will always be bounded sets in Rn from now on. If E is in 01 is Reifenberg flat, then there exists Then there exists a map from Rd to Rn such that E is equal to f of. Okay, so what am I saying? And f is Bi-Hilder. All right, so what I'm saying, okay, so E is a set. In fact, this definition, which I did not give you, and I'm about to, tells you that something is flat, and it has a dimension attached to it. So first difference to notice between this theorem and that theorem applies only to one-dimensional objects. Even in ambient space, this can be anything you want. And here, what I get is I get a Bi-Hilder map. So basically what I'm saying is that E can be parameterized by a Bi-Hilder map. Okay? So find it interesting, but I didn't tell you what this means. So let me just define what it means for a set E to be Reifenberg flat. So E in Rn is epsilon d Reifenberg flat if, okay, what do I want? It's something very similar to what I defined before, slightly, like it's a little weaker, and stronger also. What do I want? I want flat. This means that I want something to be very close to a plane, pretty much all the time. So I want that for every point in E, and for every scale, let's say like finite scale. I don't want to go like all the way out. There exists a plane, right? So this is a D plane in Rn, and is indexed on points in E and scales, such that locally I'm very close to it.
Do you actually mean a subset of 0, 1 to the n to q? Because you might have holes?
No, you don't have holes. Let me write the definition. I don't mean a subset. I mean actually parameterized by that. So what do I want? I want the set to be very close to a plane. So I want E to be very close to the plane. By very close, I mean epsilon close. And locally, so I mean the Y is inside E crossable. And then I could still have holes, but I don't, because I'm also requiring that my plane is very close to my set. So I'm also requiring that points in the plane, PXR, are very close to my set. All right, so what I'm saying is that I want that locally A is contained in the epsilon neighborhood of P, and the P is contained in the epsilon neighborhood of E. Okay? Now, in fact, a lot of the things, it's something that is very important in what I'm about to tell you, is this matter that Young brought up about holes. But for brevity and sake, like in fact, you can remove the second assumption, but then things get a little uglier, so you have to add more conditions. And let's just, if you really care about the holes, ask me later. Okay. Okay, so now at some point I will tell you, sorry, I'm just deciding where to write. Okay, I will write here. Okay, so very good. This happened in 1960s, happened in 1990. What happens now is like, okay, but maybe it will be nice to know, for instance, is there a condition that I can get on these Reifenberg flat sets to get them something a little nicer than Holder? And let me tell you, the Holder constant here is not sharp. So the Holder constant depends on, so the smaller epsilon is, the better the Holder constant is, but it's not, there is not an explicit, something like 1 minus C epsilon by Holder.
Yeah, epsilon has to be below a certain threshold, right?
Yeah, epsilon is small enough. Yeah, of course. I mean, otherwise, like everything, like this is for epsilon to be everything.
It will also tell you how small you want to have.
Yeah. And if epsilon is 0, there's only everything is a plane. Yeah. So let me like state. Okay, so what happens then? I'm gonna fast forward from the 60s and the 90s. Now we are in 2012, I think. So there is another theorem by Guy David, I don't need to write the name, and Tatiana Toro, where, well, first of all, I will not write it down, but I need to like, they do the whole Reifenberg business. So they reprove this theorem, allowing for holes in the set, which is technically a very complicated thing to do. But the way they do it is by, so the main character of the parameterization is a set E. And that was the problem, but they reduce, instead they kind of forget about the set E, and they think about the collection of planes. So their data, instead of being the set itself, becomes a collection of planes, and then doesn't matter whether you have holes or not once you have all the planes. But again, this is like highly technical, and I think that for today we can like just go over it. But in this they also actually proved something else. So they also proved that if you add some more condition to this, you can in fact get your set to be Bi-Lipschitz. So let's write. Okay, so we have always a set E in Rn. I'm gonna stop saying that is which is Reifenberg flat. There is an epsilon, there's a D. They're the obvious ones, so I will not keep writing them with me. And if moreover there exists a positive constant such that, okay, so the sum of beta infinity x rk is less than m, and this is for every x in E, and I'm summing over k, and rk is, I would like it to be 10 to the minus k, but just because that's how they proved it, this is 10 to the minus k. So I'm just like taking a sequence of scales that go to a to 0. So if this sum is finite, then f, I mean Reifenberg's f, basically, more or less, is in fact Bi-Lipschitz. And the Bi-Lipschitz, so I mean the same map that you get the older one. And in fact, the Bi-Lipschitz the Bi-Lipschitz constant is controlled exactly by this sum, but it's bad. This is like an exponential dependence. This is like, because also that one is. Okay, so I wrote this right here exactly because now it will be right underneath this. Yes.
The beta xk means an interval center at.
Oh no, sorry, this is a ball. Sorry, yeah, like I am, like instead of a cube, I take a ball. This is like remember like the picture before? Here you go. I'm now like gonna start confusing. I just wanna state things how they were written originally, but then they were like the harmonic analysis in the middle. So this with x in the center and rk there. And this has randomly reminds me that I forgot something. So this plane contains x, fun fact. I mean, you don't need to, but you probably want it to. All right. So yeah, it's just the balls instead of the square.
Could you also give one simple example for
Reifenberg flat set?
right, which is not Bi-Lipschitz?
Yeah. Thank you. I actually wanted to do that. So take a Foncas snowflake, right? That's not bad. Okay. And so the standard one, the angle is constant. Okay. Now you can make this one. This is Bi-Lipschitz if and only if the angles are square summable, because of that theorem, in fact. And by even like with other epsilon, this is flat. With epsilon small enough, this is epsilon like flat with the angle. So something like that. You should think about something which is flat, kind of flat at every scale. And how flat it is depends on the thing. Or if you want a two-dimensional example, just cross this with an interval, I guess. So like a Riemann rag, which is the other thing, that's a typical also flat set. And yeah. Does this help? I don't know. Sure. Okay. All right. So. Okay. Yeah. So what I want to say. Okay. So this sum, right? This sum here shouldn't like really surprise you because it's kind of the same sum as there. Now you should complain what I said because there is a diameter that appears in the sum there, but not in here. But notice that this for a fixed scale, I'm only using one ball because I'm summing around the point, while up there, I'm summing over all the other cubes. So you can rewrite it that without that. Again, I just like trying to write things. Okay, so great. Let me now tell you what is coming next. And after that, we'll talk a little bit about the proofs of these things, so to get an idea of how things work. But, okay, I'm going there, sorry. Doing a lot of exercise, okay. So, I'm sorry, I'm just trying to think. Okay, yeah, okay. So, we went from Hölder to Lipschitz. We went to Bi-Hölder to Bi-Lipschitz. One could wonder about other modulus of continuity. So specifically, what I wondered about was like, okay, what about C1 alpha? So this means like things with Lipschitz derivative, which are Hölder continuous, and and I want to write this here. Do I want to write it here? I didn't want to, but now I did it. Okay. So if you have a E in Rn, which is Reifenberg flat, and there exists M positive, such that okay, so we learned that when this happens from the other theorem, then we get something Bi-Lipschitz. So if you want to get something a little more than Bi-Lipschitz, I got to ask these numbers to be flatter, right? I want like something to be smoother. I want it to be flatter. So what is here, I'm going to divide by, so alpha is a number between 0 and 1. So you give me alpha, and then you check with the alpha here. So Rk, remember, is 10 to the minus k. I'm doing to the power alpha. So I'm dividing by 10 to the minus k alpha. So I'm multiplying by 10 to the k alpha. So this gets a lot bigger. But if this is finite, then that function is C1 alpha. And so is its inverse. It's Bi-Hölder, so its inverse exists. So it's its inverse. And their norm depend on this M. Okay? And well, actually, yeah, let me do it. And alpha is exactly this alpha. Okay? So so this theorem, that theorem, and that theorem, they all follow a very, very similar proof, in fact, which is like, I think I've heard some people refer to it as like the Reifenberg algorithm. Not really an algorithm, I think from the technical point of view. And I think like maybe like I spent just like a couple of minutes just try to tell you how the proof works. The idea is like very simple, so nothing too technical. So remember what I was telling you from here, right? So you have a set E, but instead like you also have like all this family of planes, right? So you have like locations and scale, and then you have like a set of planes. No, okay. And so what I want to do, I am constructing all these theorems are constructing. I'm building a parameterization with the hands. So what do? You're like, okay, so in a ball of this size, maybe we should use a different color. I have a certain, I know like at this point, at this scale, my definition gives me a plane. So here's my plane. And now I'm going to say, okay, so I'm going to take a smaller scale, like a 10 to the minus k net of my set. And so at this scale, I just see a line. And I say, okay, so this is my first approximation of f. Okay? Now what I'm going to do, I'm going to go to the next scale. And now I'm going to see like all other smaller scales. And now in here, each of them comes with its own plane, right? Because now I'm gonna, but now what do I know about this plane? Well, can the line be something like, can the new plane be something like that? They can't, because they will violate all these angle conditions, because in fact those provide you some coherence between the planes. So what is in fact you can get is that all the lines next are gonna be something like this. They make a very small angle. And so now you define a new map, which is taking like the projection onto this line with some nice gluing over here. Okay? And now you can continue going down in all the scales. And so say that like sigma 0 was the projection on the orange thing. Sigma 1 was the projection on the gluing a projection onto the blue things, and so on. If you take the limit of the, if you take composition of these maps, these things is going to converge to your f. And the fact that you have controls on all these angles, how good of a control you have on the angles, is going to tell you how good f is. So if you have a control which is just that, then all the best you can, all of these are going to be Lipschitz, but then at the end in the limit, they're going to be all Lipschitz map that converge with a constant that blows up, and they converge very well. And that's the definition of being Hilder. It means to be like very well approximated by very bad Lipschitz maps. And if you actually have more control on the angle, you can actually have an uniform control on the Lipschitz bounds of those and recover it in the limit. I don't know where I wrote the theorem. Here? Yeah. Like here. And if you have even better control, you can actually study the derivatives of them. And that's how you get the C1 alpha control. So that's a really rough, vague sketch. I'm sorry if I confused you. Please ask me any question if I did. And very good. Okay. Okay, so this is like the word of parametrization, right? I have a certain amount of points in the plane, and I'm trying to find one map that passes through it and control its norm or its length or whatever. But I originally the way I came to this problem was through the word of rectifiability. So I assume I will not, okay, I will do this. I can erase this one. Just remember what the betas are. All right. So I'll write a definition, which you all perfectly know, but then it will be sense while writing. So it's that E is rectifiable if there exist maps Fi from Rd to Rn, right? Because if it's up to measure 0, countable union of Lipschitz maps. So let me just measure 0, I mean Hd of E minus the union of I is 0 and Fi if Lipschitz. All right, you're like, okay, yeah, we all know that. Very good. Okay, so now let me just like, just so it's in writing, like we could change the continuity for Lipschitz to something like, I was interested in about high order rectifiability, so something which is covered by vector maps. So I'm gonna say that something is C1 alpha irrectifiable. The same things happen, but these maps are all C1 alpha. So here alpha is the same, so fixed and alpha, but like with the normal rectifiability, this is a qualitative concept. We don't have any control on the Lipschitz constant, the C1 alpha constant, nor we have any control about how many other things. And in fact, I think, we can define, like, there is no need to define this for sets. So in fact, I would like to define this like for, I want like a radon measure mu. Is C1 alpha rectifiable if there exist F maps from in C1 alpha. And now here, I'm just gonna, instead of HD, I can put mu. So for many of you, this is gonna be like obvious, but just in case you don't like measures, this is what I mean for a measure to be rectifiable. And I just want like, and this can be different, right? So the main, like, it sounds like, okay, what's the difference? Well, the difference is that, like, in what measure am I counting the bad points? And maybe in the rest of this talk is not gonna, but okay. All right, very well. So what was happening in the meantime in the 2010, 15, 2017? People were trying to find a characterization for rectifiability. So for normal rectifiability, there is a lot more, all right? there's like all very classical results about area rectifiability. A set is rectifiable if and only if it has an approximate tangent plane, as density is 0, and projections. There is so many other things. But then in the 1990s, Guy David, after this theorem in the 1990s, Guy David and Steven Semst started the whole work about uniform rectifiability, which is kind of like rectifiability, but you kind of like, it's quantitative in the sense that you control the Lipschitz norm and you control how much of E each graph sees, like 10% for real. And in doing that, they use the beta numbers and LP variation of them. And so people then, since then, started to repurpose those uniform rectifiability tools to study normal rectifiability. So, and now that's what I wanted to write there, but I messed up. But it's okay. So this story like is a long story. I'll just tell you this, what the state of the art is for like normal rectifiability. So the theorem is in fact due to Edelen, Nibber, and Valtorta. I don't know, 18, I think. And something like that, yeah, I think so. But in fact, then it was reproved by Tolsa as well. And in fact, like, the theorem was already existed with a slightly stronger density assumption by Azam, Tolsa, and Tolsa 15. Okay, so let's assume that I have a measure mu. Mu is radon on Rn. And what do I want? I wanted the upper density, yeah, okay, sorry, of mu at x is positive, and then the lower density of mu at x is negative. If upper density, lower density is the normal density of a measure, normal Lebesgue density. So it's so the lim sup and the lim inf of the measure of a ball over R to the D.
So how can it be negative?
Yeah, finite lower, positive upper. Yes. Yeah, no.
But the lower is the lim inf, right?
Yes, I remember it by telling myself the wrong way.
Positive upper and
Yeah, so they have that's what I'm saying.
Yeah,
So they have positive and finite upper density,
yeah.
which is slightly stronger. And then Edel never Valtorta, but okay, we'll talk about that. And okay, so where do I want that? Mu almost everywhere. Then mu is rectifiable. When I don't write anything, I mean Lipschitz. If and only if. And I feel like I'm confusing people horribly, but so I'll use the sum. I wanted to use an integral now. Beta 2, I know I did not define it. Beta 2 square almost everywhere. Okay. K is still the same thing, 10 to the minus k, that's fine. What is 2 here, right? Remember, so far we only talked about beta infinity. Not your problem, it's my fault, I didn't define it. So when we took the L infinity, I raised it. We took the supremum over all points. We took an L infinity norm. Instead, you can imagine when you infimize the distance, taking an LP average of it. So should I write the definition? Or you get? Should I write? I don't know, I'll write it. Huh?
I think it's maybe a good idea to write it.
Okay, maybe I'll write it here. Yeah, I think that some people like the. Yeah. Let me write the definition. Okay, so also in a body complaint, when I define beta infinity, like if the set, I defined it for any cube, but I should have written that if the cube does not meet the set, the definition, they define them by 0, otherwise they're going to be infinity. So I'm just checking if you're paying attention. And okay, so let me define beta p mu d technically, but I'm not going to write it because otherwise of a ball centered of x on radius r. Okay, so this is So I'm going to take the distance, right? Same old thing as before. Now I have a d-dimensional plane, which and I want it to be dimensionless, so I'm dividing by the diameter of my ball, half the diameter of my ball. Then I'm taking this to the p. I'm doing an average, right? But this is a good important thing here. Okay, first of all, now I'm saying of mu, so I'm integrating in d mu. Okay, and now I'm gonna take the best plane, great, but I didn't take an average yet. I'm gonna put a power p here because I don't have to put it there.
Maybe the plane you want to put pi.
Huh? Maybe, yeah.
Plane you want to put pi.
That's why I like too many p's.
Yeah.
All right, and okay, so now I have two choices. So let me just tell them to you, and maybe like nobody cares. I mean, he knows about. Maybe he cares and knows. He's the only person that cares and knows about this, but I do. So whatever, and. Okay, so I could divide by, if I want to take a real average, here I should divide by the measure of the ball.
You're integrating over the ball.
Yeah, I'm integrating on the ball, of course. Right? So I should divide by the measure of the ball. Fun fact, in the 90s, Guy David and Steven Sams were dealing with the Alford's regular set. So Alford regular measures. So it never mattered. So they didn't use this. They divided here by r to the d, and then I also divide by r to the d, but now it can actually potentially be different, and there exist papers with both options. So whenever if you read a paper about beta numbers, remember to figure out which one the definition is. Now, of course, this is not anymore a number between 0 and 1, not necessarily. And well, because this distance is definitely less than r. So this is less than 1, and this is like an average. But when I put r to the d, no. So maybe, yeah, it was a good idea to write that. OK. And of course, like, if instead of a measure you have a set, you're just integrating in the house of measure on the set.
You don't need the other half of the Hausdorff convergence.
No. The beta is also there. There is no other half. So there's only, but in fact, like only for Reifenberg is yeah. But you're really Reifenberg flat. So you really have the other half of the convergence, and so you don't need to add it also. You don't need the quantitative control on that, and so pretty good. Okay. In fact, also in this one, which I don't know this paper by Tolsa, which was before this one, he also tells you that 2 is the only one that works because as you can very well imagine, one direction works only for p bigger than 2, and one direction only works for p smaller than 2. And 2 is the only one that gives you a characterization. So this is what I said of, okay, another Neber-Valtorta. Okay, so let me see a little, okay, so another Neber-Valtorta had this paper about the study of singular set, where they basically they in fact rediscovered these beta numbers and use these beta numbers to do something that they call this rectifiable Reifenberg. And in the paper with Nick, they just wrote it down in the geometric measure theory world, and they get weaker density assumption.
So may I make a comment?
Of course.
Something that actually is missed by the harmonic analysts on the paper by Neber and Valtorta on the rectifiability of the singular set.
Yeah.
Is that one of the biggest deals of that paper is that they don't have a measure to start with.
Yeah.
I mean,
Yeah.
The singular set potentially has infinite Hausdorff measures, so they don't have actually any measure to start with. So the magic of what they're doing is that they get in a shot by some very clever approximation technique, and by using somehow, of course, like more geometric objects.
Yeah.
There is a measure, and that this measure is rectifiable.
Yeah.
So you could somehow split, of course, that paper into 2 parts. I mean, one part would really be like the Assam Tolsa.
Yes.
But there's a previous part in which they're actually able to get a measure to start with, which is they're able, for instance, to bound the Hausdorff measure of the singular set.
Yeah. That's the.
Of say.
That's the part. That's the part I don't understand.
Which is really remarkable because the rectifiability, for instance, was known by the works of Leon Simon.
Yeah.
But Leon wasn't able to actually estimate the Hausdorff measure.
Yeah, and they also get packing bounds, right, or something like they also get yeah.
bounds, it works
Yeah, but like the
without,
part how to get the measure is the part I don't understand. So
it works
I'm,
without analyticity for harmonic maps, for instance.
yeah.
So there's a lot of
Han had things for had something like, I mean, more like in the Simon style about harmonic maps from the 90s too, and he actually used Reifenberg as well, like Chin Han. Yeah, he has like some stuff about harmonic maps where he uses but without like but without it saying that's the part. That's why this is brilliant. Like, I mean, also this is great. I'm just saying like that's the.
Sorry?
What's the theorem about harmonic maps?
Well, the theorem about harmonic maps is that so if you have an harmonic map in a C infinity, or C infinity target, then the singular set is going to be rectifiable and has Hausdorff measure, which is finite. That is the part.
Yeah, I actually knew that. I just wondered whether everybody else did.
Ah, okay.
All right. Yeah, that's my goal in life is to learn the other half of these results, right? So I understand half of it, and then like not in life, but like in the short-term life. Well, okay, never mind. I'm just gonna stop talking. And all right, so this is what the theorem state of art I defined for you. Let me push this up, maybe. I don't remember what's written here. Oh yeah, we can erase this. Okay, so and now I wanna. Okay, I wanna state you like, okay, so I told you like, so this is like the best you can, like, this is great. This theorem is like from this type of math point of view. So another question is like, okay, but what about T1 alpha map? Can I do something similar? And so let me, so I want to find some sufficient conditions in this case. So I get, so mu is a random measure on Rn, which satisfies the density assumption in star. And then, I think, okay. Then, if I'm gonna, I'm gonna get some conversions on the beta numbers. So let me xrk. Oh, but I'm gonna divide again by rk to the alpha square. If this is finite, then mu is C1 alpha rectifiable. Right? So this is in line, well, this should be like exactly what you were expecting at this moment. Like they should have enough data to, and this is like in line with this thing. This is great. And the sum is the same sum as this one. And I can just tell you, waving my hands for 1 second, how the proof works. And you just take the support of mu, and then because of your good density assumption, you just chop it. And it's not really stopping time, but you chop it, and at the end, each of the small pieces is Reifenberg flat. So you apply, what is it? I lost it. Maybe here. Okay. All right. You apply this, and then you take a countable union, so you get the rectifiability. And the density, so that's like really waving, but that's like, and that's somewhat like a standard way of proof. Now, something that you will be very disappointed by is that this arrow only goes in one direction, and maybe like this is.
How do you deal with the holes though, right? So because in there,
you chop it in like smaller half-force regular pieces, because like you use this. Well, you use that because you start with the rectifiable. Like if these hypotheses are true, those are also true. So you already something which is already rectifiable. So you already know you're covered by Lipschitz images.
Okay.
So like you actually use that.
Okay, you actually use.
You already know that you're rectifiable. So you're really like nice. Yeah. Otherwise, if you didn't know you were rectifiable, you would have to work a little harder to deal with all the holes.
So then you want to show that the graphs, which are covered in somehow, they actually get.
Exactly. Since you only want everything like you're covered by it. You don't like. So yeah, exactly. You like using that theorem in the proof is like crucial to like make life way easier. And okay, something you should be a little disappointed by is that this arrow only goes in one direction, and like the theorems which are nice are the theorem which give you like the theorem which I like is a theorem like that which give you a characterization. Is something like traveling salesman will give you a characterization. So one question to ask is what about the converse? Okay. Also, yeah. Also, you can find but I'm not gonna write. I'm just gonna mention it. But like you can find so there exists some geometric objects called Menger curvatures, which in one dimension are nice and pretty. Otherwise, they're kind of a nightmare. But like German not theorists really like them. So there is this like instead of a condition implying beta number, if you are a German not theorist and you don't like beta number, you can replace this condition with Menger curvature and obtain the same result. And this is a joint work with Max Gehring. So if you replace this with Menger, basically, and it's very vague. I'm just gonna, I guess this now, okay. And it's something. So just like okay, just to mention this. Okay, so now one question which I really wanted to understand was what about the converse? Like, is this like a only sufficient condition? Because let's look at this like in the parameterization case, right? Both the okay, here it is. Like things which are smooth don't really need like Reifenberg flat is a very strong flat conditions. It means that you're flat at every scale. So I believe that Reifenberg flat is like overkill, like you're requiring a lot because really like you cannot curve at any like you cannot like it's really flatness at every scale. But here we don't have Reifenberg flatness, so it's a good. I thought it was a good question to ask what about the converse. And so I'll put this up and this down. So if I have a question which is C1 alpha rectifiable, is the sum finite? So question, and the answer is no. So that's not true, okay? So maybe if I would like to spend 5 minutes trying to show you the counterexample, but I think it's cute and should be, I'm not going to tell you the computation, but I think it should be very understandable. So to find the counterexample, what do I need to do? I need you to provide you a C1 alpha rectifiable measure, for which the sum is not finite. But I'm going to do more. I'm just going to provide you a measure which is C infinity irrectifiable, but such that this sum beta 2x rk to the alpha square is finite if and only if alpha is 0. So this is infinitely rectifiable, so it's definitely Lipschitz rectifiable. So we already know that if alpha is 0, this thing is going to converge. I'm telling you now that alpha is going to work. So, and all I'm going to do is a picture here. So let me do this. And now the picture is everything. So if you get confused, please stop me. Okay? Also, I'm bad at drawing, but maybe squares, I can still do it. Okay, so let me take the segments 0, 1 in R2. And now I'm going to take the Whitney decomposition of the box above it, right? So like, oh God, I'm very bad at this. Okay, and now I'm taking the Whitney decomposition, right? So what is a Whitney decomposition? Okay, so if you don't know what a Whitney decomposition is, just very briefly, is a decomposition of a complement of the complement of this in this box, so that each cube is roughly, well, in this case it's exactly, each cube has the same distance from my set, then its diameter. So this is diameter 1 and this. And my set, let me draw it in red maybe, is, I'm going to call it L. Okay, and now I'm going to define a measure. So I want to put, in each box, I want to put a segment. In fact, they could be delta masses, but people like, in this way, it's like absolutely continuous, so it's nice. So you can just put like, okay, all these segments. And now I'm giving to each of these segments a weight mu k. So here I give you mu 0. Here I give you mu 1, mu 1, mu 2, mu 2. You got it, right? Okay. And I'll tell you what this is, okay? And too much choice, okay. And so let's like, okay, and this is my measure, and my measure mu gives mass 1 to the unit interval, okay? So my measure mu of all of our plane is going to be, well, it gives 1 to L, and then I have to sum one time this, 2 times this, right? So then I have to sum 2 to the k. Well, okay, I guess 2 times. Okay, I'll call this mu 1 and this mu 2. Okay, you got it. Okay, so this is my total mass. And now I want to choose this so that this mass is finite. So for instance, a very good choice for that is if I choose mu k to be 2 to the minus k times 1 over k squared. Okay? And now, and this is something which was like really from a paper of Badger and Schul, where they compute like Jones function or whatever. You have a very specific measure, right? So we can compute the betas. You can get pen and paper and do all the computed betas. You can sum the beta square and blah, blah, blah. And what you are going to get is that basically the sum of beta 2 xr k squared is comparable to mu of r. That's basically what the computation will give you, and this shows you that, and if you divide by alpha, this is going to blow up. So it shows you that like that sum is not going to be finite for a alpha positive, so that this theorem does not have a converse. But personally, I think, as I said also in September, and I've been doing some progress in that, and that I think that this is things that go wrong is because we have all these countably many things. I do believe that there should be a C1 alpha version of that theorem, where I can give you a condition on beta, and which is satisfied if and only if you're a subset of a C1 alpha curve. And I think I will stop here.